against the content object name that they're going to produce. And remember that when the initial interest came in with no sequence number on it, that prompted the producer to pick a sequence number. So each producer randomly picked a sequence number. It looks like this one was 279027, and the other one's hiding, but they all picked a sequence number. But after that, they should only be responsive to subsequent interests in the next sequence number. And that means that only one of them can really answer the interest.
Is there a possibility that two customers may receive contents from two different producers?
Is it possible that two consumers get content from two different producers?
These two consumers are close together or far from together?
It is possible.
Yeah. We can show that happening here. It goes to a different part of the matching. So if Jim started all three producers up again, the one that got picked was, let's see, we had 27 sequence number, 79, and a 63. 63 got picked. So it's sort of in the middle of the sequence number range. If he had started this up again, the producer is going to pick a random consumer, so we pick the first consumer that gets back to it, and that might go into sequence number. But each of those guys got to put something in the content cache. If you started up another consumer, then its first request is going to get satisfied out of the content store. And the request that's satisfied out of the content store is the, when you've got a choice of multiple children of a node, so you've got this line maker node, and then you've got a bunch of seven. The default rule is you pick the least magnitude one. So there you're deterministically going to pick the lowest sequence number out of the different producers. And every consumer that you start after that is going to be biased by the content store to get the lowest sequence number. Except for the first guy who gets to see a random one because there's nothing in the content store. So that default ordering rule will pick one out.
Yeah.
Why there are three?
Well, yes. Okay. So this is the million-dollar question that I've been pondering as well. Why do these? So it's clear that this one, the one starting 6.3, basically won, right? And got to supply most of the content object. Why were 3 made, apparently, by the other 2?
Check Michael's code, because I don't think he was checking the sequence number in the interest.
Aha. So maybe he was not checking the sequence number in the interest. And just to make things more complicated, right, this is actually not exactly the same program that we looked at before, because this is a program that's trying to do the producer rate limiting, and the one that we looked at before didn't have that feature. So let's see. Now, sadly, a consequence of that is that this program is considerably more complicated, and we weren't necessarily going to go into all of it in detail, but let's have a quick look at the interest handler.
Oh, the 3. No, that's the size of this little bit.
Oh.
Yeah. So it's the way.
Okay, so this is adventures in making examples in a hurry for things that we haven't done before. And it probably would take me longer to explain why this is the way it is than it's actually worth. So the reality is that this producer program keeps in its own state a little bit of memory about interests that it has seen. And this is related to the way that the rate limiting was done to get things to be even in the model that he was using. So it's like it has its own little pit inside its program, not CCND, but inside its program. And the size of that little pit is 3. You see it?
Yeah. CS doesn't matter, only
Right.
whoever we use, but it says 3 hit entries and the not correct logic in the.
Yeah.
in the
So I think that, probably the overall answer to this is that this is sort of a bug in the producer program.
It's not sort of like a bug.
It's a bug in the producer program. Yes.
I have another question also related to routing. And you mentioned just now that when the producer is start up to register to the customer's FID. So the question is how? Actually, in a more complicated network, for example, when the producer is very far away from the consumer, so how does it update all the
Right.
FID in the routing?
So that is in fact a routing question, and it's separable from this registration that's occurring here. So the registration that's occurring here is an entirely local operation to the local CCND. Each of these processes is running on the same machine, and it gets a local type phase on which it can do a registration. And what that basically says is, if routing elsewhere in the world points interests to this CCND, here's a local process to send them to be satisfied. Okay? That registration happens in the startup. It's some of all of what we saw scroll by with lots of hex and things in the log from CCND. So it's a specially formatted interest that encodes the instructions to CCND about how to set the fib and what the prefix should be. But it's purely local. That never propagates off of the machine. Having that information on the local machine could be an input to a real routing protocol if you wanted to set up your routing protocol that way. Or you could set up and do routing separately. And you have to solve the routing problem for a large scale, wide area.
So it's not cycling or not fixed yet?
No, and not by this. There is work going on in the NDN project. For example, we have a implementation of OSPF for NDN that will communicate information about reachability of NDN prefixes using the OSPF, the existing standard OSPF protocol. But that doesn't come actually out of registrations at this point.
That question's probably a good place to bring in another point about name engineering. So we're just picking the name line maker that identifies the service. That name could be arbitrarily long. In particular, in the front of it, you could put the topological information to make routing work. So we could stick a prefix on it that said snu.ac.cr/linemaker, or it had the prefix of this machine. So what that would mean was we were buying into the internet DNS prefixes to do our routing, or the internet address prefixes to do our routing, and we would put those prefixes on the front of our names so that things far away would be able to get the request to our local machine. And then our local machine would start looking at the line maker, and that would get it to the process that could service it. And that's the scheme that we're using on NDN, that we've set up prefixes for NDN Park, NDN UCLA, and when we're audio conferencing, we create the media streams in our local sites namespace, NDN/Park for us. In order to discover the other participants, you also need to be able to do broadcast announcements. And for that, we've got a /NDN/broadcast, which is floated everywhere. So another part of engineering the namespace is doing the topological engineering for getting the data to to where it needs to go. And you can engineer in two ways. You can decide whether it's going to be unicast or more multicast, and then you can decide for the stuff that's going to be unicast at what sort of granularity, how much hierarchy you put in. For example, UCLA's got a couple of subsites, they've got some hierarchy. And it's another, all you've got to work with in NDN is the names, but you've got incredibly powerful names. You can put almost anything you want in a name. We have this working, very scalable internet forwarding model that rests on longest match lookup. So you take an address and you match as many bits as you can, get the longest match, the detail max, and the fifth. So the combination of these very expressive names and longest match lookup lets you do at least as well as, and generally better than the internet for scaling. If you want to solve exactly the same problem, we can do it with less state than the internet does because we've got more expressive names and we're using the same model. But it rests on putting the topology information on the front.
So I'm going to summarize a little bit of that as well with an example of a different, more elaborate name that we're not actually using in this example. So Ben talked about the topological part. So by taking advantage of prefix matching, we can use the front part of the name for topological purposes. We've seen in this example case of having a fixed part of a name. This is just a string, a constant string, always the same. That's part of the name designed for this application, and the agreement between users and consumers about how data is named in this application. We've seen an example of a sequence number part to a name. And this is a case of something that's part of how we name segments when we take a whole sequence of things and break them up, and is the sort of thing that you might imagine very many applications will have a need for this kind of thing. And so you might imagine, and you would be right, that this is the kind of function, piece of naming, that can be supported with library support, so that applications don't have to reinvent it all on their own separately every time they do it. And so you find these different kinds of pieces of naming all appearing in your applications, often topological parts at the front, some sort of constant and functional sort of parts of names that are really chosen by the application in the middle, and then oftentimes some use of very reusable conventions for the later parts of the names that distinguish things like segments and versions and temporal evolution. With that, we need to take a break. So we want to take a break until, at least until that clock says 4, probably 4:05 on that clock, and we will figure out how we're going to navigate the next bit. So thank you very much.